Hey guys, how you all doing? Wanted to do something a bit different today, so I thought I would do a quick video on what I know about DC applications. Currently I'm employed by a fire apparatus company as an electrician, and I wire up some crazy stuff. Switches, reversing motors, deck guns, chutes, ladder, I mean, it's just, there's a lot. But anyway, I've seen a lot of videos and I've seen a lot of people ask questions about stuff like this that go unanswered, so I thought that I would start maybe a series on how to do wiring in your car, your ATV, your motorcycle, whatever. So, enough of the boring talk. I'm going to get right to it. This is a 12 volt DC battery. DC stands for direct current. The type of current that's in your house is AC, alternating current, which means it's delivered in a wave kind of form. DC current is pretty much flat. So if you want to check for voltage in a DC current, you need a 12 volt test light. And there's a lot of DC currents. The older tractors and systems, cars and so forth, were like 6 volt. Most modern stuff is 12, however there is 24, 36 volt and so on. But anyway, to test a 12 volt system for voltage, basically a test light will do, and you touch one end to the negative, one end to the positive side of the battery, and your light will illuminate if you have voltage. Now the cool thing about DC is, doesn't matter which side you connect, you're going to show voltage. So you know you have voltage in your battery, but most 12 volt batteries in an idle state are 12.5 to 13 volts. So how many volts do you really have? You're not going to know unless you have a voltmeter. So this voltmeter is a snap-on. I've had this for some time, and it's got multiple settings, I guess you could say, for testing various things. The first one is AC voltage, and you probably can't see that, but it's that wave symbol over a V. That's not going to give you the correct voltage reading on your DC system. So obviously that's not even close to being correct. Zeros across the board. So you're going to want to choose your DC voltage setting, which is a straight line with a hash line underneath it. And testing that is going to show that we probably have around 12.5 volts in this little battery. So we have 12.56. And again, the cool thing about DC voltage is you can check for voltage backwards. It's going to show you basically the same reading, but it's going to put this little minus sign in front of the numbers. And that just lets you know that you've got your meter hooked up backwards. So as a time-saving thing for this video, I've already done all the connections, and I'm going to show you how to connect a very simple circuit, which is your battery to a switch that's going to control a light. Now this light could be an LED on top of your ATV, it could be an additional set of parking lights in your car, it could be a stereo, it could be pretty much anything that you would like to control with an on and off switch. And that brings me to the switch itself. This is a simple 2-connection switch which does 2 things. Creates a circuit or breaks a circuit. For anything electrical to work, you have to have a complete circuit. Typically 12 volt flows from negative to positive in this direction, and the switch needs to be turned on to complete the circuit. If you can think of a switch like a garden hose, if you have the valve shut off, there's no water coming out of the hose. If you turn the valve on, water is flowing, very much like electric. The switch is off, there's no water flowing. You turn the switch on, and the water is able to flow through the hose and do whatever it is you need it to do. So, the switch is inside sort of like this, and that would be on. Off, when you flip the switch, it takes the two connections away and breaks the circuit, thus prohibiting the flow of current, voltage. And it shuts off whatever it is you're trying to control by the switch. So turning the switch on, you'll see that our light works. Turning it off breaks the circuit and the light goes off. All electrical components have an amperage rating. These little bulbs, this is an 1157 bulb in the wrong socket, but it still works for our purposes. I don't want to confuse anyone. Anything electrical should be protected by a fuse or a circuit breaker. Now, a fuse comes in 3, 5, 7.5, 10, 15, 20, 30, 40, 50, 60 amps. And this fuse, and I really hope you can see inside of here, this wire comes into this side of the fuse holder and is separated from the other side of the circuit. The fuse makes the circuit complete. Inside of the fuse is a bimetallic strip that is rated for 10 amps in this case, which is much more than this bulb needs, but it's what I have on hand. So if the circuit were to exceed 10 amps, this bimetallic strip would get hot and it would melt, therefore breaking the circuit. That would protect your wiring, your components, your switch, and so forth. When you put the good fuse in, it completes the circuit and allows your component to function when you turn it on. For anything electrical to work, you have to have a complete circuit. I don't recommend putting anything in that is not protected by a fuse or a circuit breaker. A circuit breaker is a little bit different in that the bimetallic strip is much like a switch, where it's connected, completing the circuit when everything is optimal. If it gets too hot, that bimetallic heats up and bends and pulls away, breaking the circuit. When it cools off, it closes the circuit again and allows the component to operate. So if you have a light, a radio, who knows what it is you're wiring, but if it's doing this without you touching the switch, and you have a circuit breaker in line, the chances are pretty good that the circuit breaker is too low of an amperage rating. Let's say that your component requires a 30 amp breaker and you have a 10 amp breaker. So the component is drawing more than the circuit breaker is willing to give. Or you have your positive side shorted to ground. Ground is your negative, positive is your power supply side. And the circuit breaker is going to react to that. That's how a turn signal works in a car. Turn signals use this little canister type thing that's called a flasher. What happens is it's rated at a low amperage, so when you turn your turn signal on, it heats up, breaks connection, rapidly cools down, reestablishes the connection, breaks, reestablishes, breaks, reestablishes. So you're getting power to your turn signals so that they blink. A couple of quick things about connectors. And again, I know I'm rushing through this, but hopefully it's not going to be a 4-hour video. Connectors come in all kinds of different types. These are heat shrink connectors. These should be used anytime your system may encounter a wet environment. And the colors are the ones that I buy anyway. These pink ones are for smaller gauge wires, 18. The blue ones are for a little bit heavier wires, like a 14 gauge. The yellow ones are for like a 12 gauge. If you're real careful and patient, you can get a 10 in here, but it's tight. And you want to make sure the connector fits the wire. You don't want to stuff it in there with half of the wires in the connector and the other half not, because that puts an undue stress on the wire itself. Again, pink, but the larger connector is good for like a 10 gauge. You can even get an 8 gauge in here. These are all shrink connectors. Again, only used for wet conditions. Under the hood, under the truck, under the car, if you're hooking up trailer brake or trailer lights or something, you definitely want to use these, because they make these as well, but these are not heat shrink. And what happens is moisture, water, rain, salt, road debris gets inside of this, and it will eventually corrode, probably turn green, break and fall apart and no longer function. These are household connectors. You'll find these in your breaker box, you'll find these in your outlet boxes, your switch boxes. These are not meant for vibration, and they are definitely only meant for dry areas. The metal inside of these that is used to twist the wires tight, I've seen these on automotive applications, and the metal inside here does not last very long. It rusts, it falls out of here, and you either wind up with a short or a broken connection. So do not use these in an automotive application. The ones that I was just describing, these heat shrink styles, now I don't have my normal little torch that I use at work, but I intentionally left this one unshrunk, untreated, unheated. So when you heat these up, and it doesn't take a whole lot, try not to burn the wire. You don't want the insulation exposing the copper inside. But hopefully you can see that that has shrunk around the wire and created a watertight seal. These are the Crimper Strippers that I use. And to crimp one of these connectors, I usually go right to the end of the metal. If you look inside or through it, you can see there's a metal tube in here. And your wire is going to go halfway into that metal tube. And there's a stop in there, so you don't have to worry about going too far. I usually go down as low as I can on the metal tube and then squeeze it. But you don't want to squeeze it so hard that you penetrate this plastic. That will cause a leak. Once I have my connection made, I always hold on to this end and the wire and give them a little tug to make sure I have a solid connection. Of course, you'll do that to the other wire that you're joining to this side. Once your connection is secure, you're going to melt that down like we did here. And you should have a really nice, watertight, solid connection that you don't have to worry about for a long, long time. I just wanted to make this quick video to see what the response would be like. And I will go into more in-depth things about automotive, ATV, UTV wiring systems if people are interested. But this is just the first one. So if you want to see more, let me know. If you think it sucks, let me know that too. All right, guys, enjoy your Sunday. I know this was quick, but it's, again, just the first one. I'll get more in depth if you know, y'all want to see more. Take care, guys.